Hello, today it's my pleasure to talk about multivariate optimization. What we do is we start with thinking about how we solved multivariate nonlinear equations where there were solutions. And then we just kind of tweak our thinking to where in an optimization scenario, there's really no solutions, but you're trying to minimize a particular optimization function. So we're going to talk about multivariate Newton-Raphson again. We're going to have our Jacobian, and we're going to look at an inverse versus transpose type of thing, and then we're going to bring in an adaptive gain in the way we search for solutions. All right, so remember that we've got multiple variables. So we've got n variables that are arranged in a column vector, and then we've got n functions that are functions, each being a function of those nx variables, right? And then we have an iteration. We show that with the parens. It looks like a superscript, but it's parens and with the I, showing that that's the ith iteration of the vector x, and then of the functions. And then remember, we've got our Brooke-Taylor first order expansion of the next function iteration is going to be equal to the current function iteration, the functions evaluated at the particular x, the current x. And then you're going to add in the Jacobian matrix times the change in x's from the current x ith iteration to the next x iteration as column vectors. And that's our first order expansion of the functions, of the n functions. And the Jacobian, the next x iteration, and the current x iteration. So remember, if you put it into this nice compact form where you've got that next function iteration equal the current function iteration plus the Jacobian times the delta x. So you want that next function iteration to be 0. If there is a solution, you want that and to be equal to 0. So you set that to 0, and then basically you solve for the x, the ith plus 1 x iterate, and it brings up this equation 1217, which we called Newton-Raphson. So that's the multivariate Newton-Raphson that you could use, and it works quite nicely when there is a solution. So remember, when you're searching for a multivariate root, you're looking to get this one norm of the function to come below a certain threshold. That means that this function effectively is 0. If it's to floating point error, if it gets below there, and then when it gets to a certain position where it's not changing, then you're talking about it being completely polished based on how the max epsilon a sub i's are changing. So the relative x values are not changing, so it's polished. Okay, so this is how we did that multivariate root, where we looked at the starting at this position, and we're looking for the root, the common point that exists on the ellipse and the circle. So this is how we did it. And remember that there was a breakout of the for loop that looked at how the x's were being polished, and coupled with that how the value of the function, the vector function, the one norm of it was less than the times eps. But you're not going to be able to do that when there is no solution. But in this case, when there was a solution, you see that we started our function value, the one norm of our function value started at 7, because f1 was minus 1.88 and f2 was minus 5.12 at that starting point of 1.4 and 0.4 xy. So we had that 7, and it diminished down to effectively 0. So when there's a root, then this all makes sense. But when there's not a root, we really are limited to using the book polishing method And that's what we're going to talk about now. So in this situation where there's no real intersection, so I just kind of change the circle so that there's no real intersection. There's no real intersection of the circle and the ellipse now. So there's our starting point. So if we were going to try to minimize, either one of these functions, that's the 2 norm, that's the 1 norm. I like using the 1 norm. So what we're going to try to do is we're going to try to search using this Newton-Raphson. We're going to try to search, starting there, for some minimal point. So where's it going to be? Is it going to be, is it going to be between the circle and the ellipse? Is it going to be on the other side? What's that going to kind of look like? And I'm going to tell you now, we're going to have to change how we're searching, how far we go in this direction from our current x iterate. So I call that an adaptive gain, that g value. So I'll set it to kind of a small value, and if it turns out that the function value is growing, then I'll reduce that g and try again. So that's kind of how it goes, and this was an example of what I did. I started at that same point and then used the adaptive g using modified Newton-Raphson. So it starts here, and then you see where it goes, kind of does a little juke around, and then gets back up here. So it's kind of hugging the ellipse, if you will, which is interesting and kind of makes sense because the way I'm calculating the the objective function kind of favors the ellipse. So we're going to talk about that. So if I were kind of to renormalize these things and make the ellipse and the circle weighted about the same, then I would expect to be more in the middle between the circle and the ellipse. But that's not what happened. So 200 iterations, the objective function ended up being about 0.9, and the objective function was the 1 norm of the vector of functions. Okay, so here's how I modified to solve my equations. I put into the evaluation of the xv2, the j value is really not changing here, and the function value is also not changing because I'm looking for that next iteration, the next xv2. So I'm going to be using the same xv1. It's just I'm changing the g if I need to, So I'm changing the g, and then I get the next the fv2 based on my proposed xv2 position. And if the fv2 is less than fv2, the 1 norm of the fv2, if it's less than the 1 norm of the current function, I go ahead and break, and then I use that. Then I use that xv2 and fv2. I go ahead and use it. If this is not true, then I reduce the gain. So I back off the gain a little bit, 9/10. So I start with the gain as 0.05, and I use that. I use that gain if it seems to work. But if it doesn't, I back off of it a little bit. And actually, inside my print statement, I show what the gain is. So the gain is going to be, the second variable is going to be the gain. So you kind of see how that goes. And you notice I commented out this, when FV1, the norm of FV1, the 1 norm of FV1 is less than or equal to F. So I had to comment that part out because I know there's no solution. So that's never going to be true. All right, so I'm just going to have to rely on the book polishing here with my augmented or my searching, my adaptive G here, if you will. So it's really kind of the same thing that we had before. Only things change is what I have in the red boxes. Okay, so that was using Newton-Raphson. Now I want to talk about steepest descent. And the only difference is replacing the inverse with the transpose right there. So I've got J transpose, and if you look what's happening, it's a little bit strange, but the search is always perpendicular to the current contour. So here I'm starting at my start point. You see my contour of the 5, you see my contour of the 4. So you see that I'm going perpendicular, always perpendicular, and it kind of goes down here, but then it comes back up, and I'm always perpendicular to the contour every time. And that's indicative of the steepest descent, because you're basically going straight downhill towards the objective function. And in this one, I had 200 iterations. I got to 0.75. So the steepest descent actually did better, got down to 0.75, rather than the Newton-Raphson, which got down to 0.9. So kind of interesting there. And the only difference between the previous red box and this current red box is I've got J transpose in this location for the steepest descent, and whereas I had J inverse in the Newton-Raphson version. So steepest descent, J transpose, J tick, and the Newton-Raphson was inverse. Okay? So that's how we do it. That's how you do optimization. You kind of find the point. And I talked about, just kind of going back here real quick, I talked about how it seems to be pulling more towards the ellipse. And I think the reason it is because of the 10 or the whatever that constant would have been for the ellipse. So it kind of favors the ellipse more than it did the circle. The circles had a smaller constant value there. So it's the ellipse is sort of pulling the optimization. I could have taken and renormalized it, and that has an effect here in what I'm about to tell you. So I really looked at a real engineering optimization type of problem, and this is a problem I used in mechanical design. So it's a tire iron. So we've got a load that we're applying to the tire iron to tighten a lug nut on a wheel, right? So that's the idea here. So you're applying the 150 Newton load over at point B, and then where the lug or the tire iron connects with the nut, the lug nut, is at point A, and that's where the critical location is. So that's where we're going to worry about bending stress. That's where we're going to worry about torsion. That's where we're going to worry about our failure by max shear stress theory. We're going to kind of think about a static failure scenario here and use max shear stress theory. And what we're going to do is, we could design obviously a solid, but I'd like to think about maybe we could do a tubular type of thing and see if we can make that much lighter. So outer diameter D with a thickness T. So we're going to think about doing this part in terms of a tube, and not really worry about how it transitions back to the socket part of the tire iron. Okay, so we're going to do it where we look at minimum weight. So that's one of our functions, minimum weight, and an optimal safety factor. So we want a safety factor of 3. We want a minimum weight. So what's this going to look like? What's the result going to be? What's the diameter? And what's the weight? What's the thickness? What's the weight? Safety factor is probably going to be right next to 3. Okay, so let's see how this looks. Created the tire iron in SolidWorks. Thinking about creating a theoretical cut there. The X value is coming out of the nut. I've got X, Y, Z. Fortunately, a right-handed coordinate system. I've got an H moment arm for my torque, and then I've got an L moment arm for my bending moment. Okay, so then I do like a theoretical cut. So I've got my torque value, I got my bending moment there, shear force there, Fz, and then I kind of set up some things here. Let you kind of take a look at these things at your leisure. But it got some numbers for H, L. The F is, as I said, 150 newtons. Design factor is 3, so that's going to be kind of my targeted safety factor. I got my bending moment. I got my torque. I picked a 210 megapascals for a 1020 hot rolled. I've got my unit weight of steel. I don't know what my diameter and thickness is going to be, but my A, I, and J are easily calculated if I do have a perspective D and T. So I'm going to have, in terms of my coordinate system, I'm going to have a normal stress at that top point. I'm worried about is a plus sigma B for bending. And then torsion-wise, it's going to be in the positive y direction for XY torsion, and very easily calculated. There's my sigma B is the bending moment, and then half the diameter over I, torque times the radius divided by the polar second moment of area. So I've got my equations for second moment of area, polar second moment of area, and then area. Pretty straightforward. And then I can get my principal stresses pretty easily. The sigma 1 minus sigma 3 is going to be 2 times the square root of sigma b, of half of sigma b squared plus tau tor squared. So very, very straightforward to get my numbers here. And then the idea. So I'm going to have two functions here. I'm going to have, I'm going to look at, sort of this right here. I want this to be 3, exactly 3. So kind of fudged around with this a little bit and tried to figure out how I wanted to do this. I ended up kind of normalizing it too. So I took, okay, I want F1 to be 0, really. And I had to be careful. I don't want it to be negative, but I definitely want F1 to be a positive value. But I went ahead and showed it as absolute, and then I had to go back and check to make sure it had the right SIGN. But SY minus 3 times the sigma 1 minus sigma 3 divided by SY. So I wanted the numerator to be 0, and I went ahead and normalized it because comparing F1 to F2 got a little bit unwieldy because my weight, if it were solid, completely solid, the first 2 lines, my weight's like 14.5 newtons. So that was going to be kind of unwieldy to compare that with this being, very close to 0. So I normalized that, and then I tried to kind of compare them. So what I did is I took F2 and just divided it by 10. So I tried to balance it by taking F1 and then F2 divided by 10. So that's what I tried to actually minimize. F1 absolute plus F2 absolute divided by 10. F2 is going to be a positive weight, so I'm not sure that I should have fretted with the absolutes, but to make it a 1 norm, that's what I did. Okay, so these were some values that I had put through the ringer before I even considered this class and this optimization. And I went ahead and did my fully solid one there and got a factor of safety of 3.55 and a weight of 14.5 newtons, right? And then I repeated with a tubular version where the 22 millimeter for my diameter and then 11 for my thickness, which would be a solid, right? Because the thickness would leave no hole. So these were the same. So that vetted in my mind that my analysis was right. And then I poked around and found a 38 millimeter diameter with a 1 millimeter thickness. And I found that to have a factor of safety of 3.56 and 4.4 newtons. So significantly less weight and actually the same safety factor. So this was my starting point, and I felt pretty good that that it was right. And now, kind of set up to kind of start, using my optimization techniques that I've been showing you guys today. Okay, so the first thing that I did was I did F1. I just wanted to kind of plot what F1 looked like, and I got over here and expanded it. Just wanted to make sure that this made sense, right? So I did the SY minus 3 times sigma 1 minus sigma 3, so that's sigma B, sigma A. So I'm looking at this green rectangle here. So I'm picking up my SY is 210, right? And I'm subtracting off 3, my ND, and then I'm going to multiply the 3 times 3667 minus a minus or plus 2236. So that's how I got that. And I do quantity, and then I divide it by 210 again, just to make it normalized. And I got a value of 0.15. And when I go over here and look, 38 with about 1 millimeter. So that's where I am, right? 38 and 1 millimeter. And it's and I'm close. It's showing 0.16. So I feel like this is working. And you can see the contours, right? You can see where I am right now is 0.156. So looks like there's some kind of little valley here, right? So there's a valley that kind of goes here and scrolls back through here. I definitely don't want to be out here, right? So I want to be kind of rolling in this area, rolling in this area. So I see it right in here. I don't really want to be over here. That's where, it's showing it as a positive, but I think that this actually would be on the wrong side of 3, the way that this is kind of working out. So I want to be, this is that valley I think that we're talking about right now. I want to be on this side of that valley. Okay, so that's taking care of F1. So that's what F1 looks like. Okay, let's go look at F2. So F2, I've got my weight, and you can see how I've kind of given the weight function here, F2. See exactly what that is. And you can see that so kind of the same kind of thing where there's going to be a slope going on here, almost the same shape of curves, interestingly enough. But, of course, as my thickness goes down and down and down, my weight is going to go down and down and down. And I picked up again, tried to pick up near the 38 and 1 just to kind of make sure I'm that I'm doing this right. And 38 and 1 gives me that 4.45. And you can see I am above 4. I'm not quite up to 1. So I'm right in the ballpark. So I feel like this is all working, right? It's all working. Now I'm going to put the F1 and the F2 together and see what that looks like. Okay. So I did 2 contours. I did F1 is red, and I just wanted to show that 0.01 sort of crest or valley that not crest, I beg your pardon, valley that we're kind of looking through. So I think that these are very much parallel to the weight contours. So it's going to be kind of tricky to find a good value here. I think if you just keep going, bigger diameter, very thinner wall, you're going to just very quickly get down to maybe 2 newtons here. But anyway, so I did a couple of things here. I looked at the 38 and the 1 again. 38 and 1. And this is this over here. So this is going to be F1 plus a tenth of F2. So that's that objective function I was telling you about. So right there is where I'm kind of starting, right? So that's going to be the 38 and 1 millimeter, right? So 38 and 1. And then I was looking at, well, what if I did 35 and 1? That's going to be a little bit less. That's a 4.09 Newton. All right, so it's going to be over here. And then the very last one I did was 40. I looked at 40 and then about 0.75 millimeters, which is 750 microns. So that kind of level. And I got I'm writing this crest, or I'm sorry, not crest, but valley, right, in the objective function. So that's what I'm doing. So I was able to find a place there, 40 millimeters diameter, 750 microns or 0.75 millimeters of thickness. And I'm looking at a factor of safety of 3.02 of the 35 millimeter diameter with a 1 millimeter thickness. That had a 3.0 factor of safety. Now I've got 3.02. So I'm right there at 3. I'm right there at the optimal factor of safety. I've got the optimal factor of safety, and I'm just kind of riding this crest here. I could keep going. I could go to 42, and the thickness would be probably around a half of a millimeter, but I could get the weight down even more and keep that factor safety right at 3, so I could kind of ride that. But all of this is coming about from analyzing it from that optimization perspective, where you're adding a certain weight for F1. You're adding that to a certain safety factor is embedded in F1, and then F2 takes care of the weight. And I'm only taking 1/10 of that because the weight is considerably bigger in magnitude than my safety difference. Okay, so anyway, so that's how you can do this. You can put the optimization techniques that I've shown you. You can put that to good use on a real type of problem, and that's probably about the best one. I figured I would stop there. Okay, so 40 millimeter diameter. I've got 750 micron thickness, 3.5 Newton weight with a factor of safety of just above 3. So okay, so anyway, so we looked at a multivariate nonlinear optimization. We looked at using Newton-Raphson. We looked at using Jacobian. Inverse would be Newton-Raphson. Transpose would be steepest descent. We had to talk about using an adaptive gain, and then we finally looked at that the tire iron, a real world example. It just the quirky thing there is that you didn't have you had these things that are kind of parallel, very 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 close to being parallel, where the weight contours and then the safety factor contours were very close to being parallel, but we're still able to kind of find something there. So I hope you enjoyed it.